Welcome everyone. I'm going to be going through a review for the quarter 4 assessment in Algebra 2. And I'm going to begin by talking about power and root functions. This is the unit that we talked about where we had rational exponents, where you might have had exponents that were fractions. In fact, most of the fourth marking period has been dealing with rational expressions. And rational, if you just remember, it rhymes with fraction. So a rational expression is just a fractional expression. So the first thing we want to take a look at are the rational exponents in problems A, B, and C. The same numbers are being used, but we're looking at these expressions from a different lens, and the notation is a little bit different, and so I just want to make sure that it's spelled out very clearly how you would simplify these expressions, because this is something you need to be able to do without a calculator. So let's take a look at the difference between some of these expressions. You'll notice in letter A and letter B, in letter A we don't have parentheses around the -8, but in letter B we do. In letter A, it's really important when you don't see the parentheses. This expression is telling you to take the opposite of 8 to the 2/3. So the negative is something that's actually on the outside, and it's not going to be impacted by the exponent. Another way to look at this is to look at it as -1 times 8 to the 2/3. And then if you have to simplify 8 to the 2/3, remember when you have a rational exponent, the number on top is the power, and that makes sense. If it's powerful, it's going to be on top. And the bottom number, the number underneath the fraction, is going to be your root because it's underground. So if that helps you remember which is which, the power is on top, the root is underground. So I basically need to figure out how to take the cube root of 8. And it's usually easier, especially if you don't have a calculator, to deal with the root first and then use the power. So I'm taking the cube root of 8, I'm ultimately going to square it, and then I'm going to multiply by -1. And that way, I'm following the order of operations, and I will simplify this correctly. So when I take the cube root of 8, I'm thinking about numbers that when I multiply it times itself 3 times, I get 8. So the cube root of 8 is going to be 2. So this expression is going to simplify now to 2 squared, and then again, I'm taking the opposite of that. And 2 squared is just 4. So ultimately, I'm going to get -4 as my answer. So obviously, you don't need to show every single step. This is something that you should be able to do without a calculator. But I really want to emphasize that when that negative is not in the parentheses, it's not being included with that rational exponent like it is in letter B. So when the negative is out in front, think of it instead as taking the opposite of the expression. So if it's a positive expression, you know your answer is going to end up being negative no matter what. In letter B, now the -8 is in parentheses. That means when I take my expression and I deal with my root first, that cube root, the -8 now is underneath. I'm still ultimately going to square it, but now I want to think about numbers that when I multiply it by itself 3 times, I get -8. So that is just going to be -2 times -2 times -2. We know the cube root of +8 is 2. Well, if I have an odd root or an odd power, if the original number or the base is negative, my answer is going to be negative as well. So that doesn't change. So when I take the cube root of -8, I'm going to still get the -2. When I square it, though, that's just going to be -2 times -2, which ultimately ends up being a +4. So notice that letter A and letter B, even though they look very similar, produce a different answer. And it's important that you can make that distinction. Letter C, you'll notice, is ultimately the same thing as letter B, because the -8 is the negative is included with the 8 underneath the radical. So when I take the cube root of -8, I get -2, and then when I square that, I get a +4. Okay, so I just want to make sure that everyone's clear about the different ways that we can express the quantity, and that having those parentheses around a negative number are important if that's what you need to do to solve the problem. All right, and number 2, we're looking at solving equations that involve rational exponents or radicals, or just powers and roots is how I refer to them. So if I take a look at any of these expressions, what we want to do is isolate the expression that involves x. You'll notice that in both situations, there's only one expression involving x. I want to get that expression by itself. If it's under a radical or in parentheses, I can't move. For example, in letter A, I've got that quantity x minus 3. I'm not going to be able to do anything with that -3 until I've taken care of the rational exponent. So we're essentially following the reverse order of operations. So while addition and subtraction is something that we tend to do last, past, when we're following the order of operations, it's usually the first thing we want to do when we're solving an equation, because I'm inverting what happened to x. So let's take a look. If I've got x minus 3, the quantity, raised to the 2/3 power minus 4, and that equals 5, I'm going to undo what's happening. So I'm going to go ahead and add 4 to both sides, and I'll be left with x minus 3 to the 2/3, and that's going to equal 9. The one thing I also want to take a look at with that rational exponent, I've got a power of 2, so I'm dealing with an even power. And then the 3 underneath tells me I'm also dealing with an odd root. With the odd powers and roots, you don't ever have to really worry about the sign, whether it's positive or negative, because like we saw before, when I take the cube root of a negative number, I get a negative number. The same is not true when I'm dealing with even powers and even roots. With an even power, if I raise something to the second power, if I multiply a negative number by itself, it's always going to come out positive. But with an even root, I've got to be careful because I can't take the square root of a negative number and end up with something real. I end up with an imaginary number. So one of the things we do have to remember when the number on top is even is that I'm going to have 2 answer choices. If you remember from the beginning of the year when we were talking about quadratic equations, if you saw something like x squared equals 4 and you took the square root of both sides, you had to remember that x could be a positive 2 or a negative 2. The same is going to be true here, even though it's not quite as obvious because of that rational exponent. But when the number on top of that fraction is an even number, you've got to remember there's going to be 2 possible solutions. And so when I'm undoing my rational exponent, since this quantity, x minus 3, is being raised to the second power, but it's also being cube rooted, I want to invert both of those. So I need the third power to undo the root, and I need the square root to undo the power. Well, I can do that all at one time. I'm going to raise both sides to the 3/2. And the 3/2 now, if I multiply if you remember your exponent rule, if you raise a power to a power, you end up multiplying the 2 exponents. Well, when I multiply 2/3 times 3/2, my exponent ends up canceling, and so I'm ending up with a exponent of 1. So what's nice about that is now it kind of unleashes the x minus 3. It no longer has to be in those parentheses. When I take 9 and raise it to the 3/2 power, remember, it's easier to take the root first. So think of this as the square root of 9 raised to the 3rd power. Well, the square root of 9 is 3. And if I raise 3 to the 3rd power, then I've got to take 3 times 3 times 3. And that's going to be 27. But it's at this point that I've got to remember that plus or minus. So I actually have 2 answers here. It's not okay. A lot of students will add 3 and then put the plus or minus at the end. It's at this point when you've undone that exponent that you want to take care of that plus or minus. So I find it easier to just separate the problem at this point. So that means x minus 3 could be a positive 27, but x minus 3 could also be a negative 27. And so then I'm just going to solve each of these remaining equations. If I add 3 to this equation, I'm going to get x equals 30. If I add 3 over here, though, I'm going to get that x is equal to negative 24. And that means there are 2 possible values of x that will satisfy this equation. And one thing that it's always a good habit to do is to plug your answers back in to make sure that they work. Let's take a look at the next equation. Now I've got the square root of x minus 1 plus 18, and that equals 8. One of the things that we have to be really careful of when we have even roots, if you remember, the domain of this function is not all real numbers. If you remember, the parent function looks like this. So my domain is what we would say is restricted. My domain is going to depend a lot on my horizontal shift. If you remember the a, h, and k values, that h value shifts the graph left and right, and that's going to impact the domain of my function. The thing is, when I solve the equation, even if I do all the math correctly, I may end up with an x value that's not in my domain. So when you're dealing with even root functions, and this is an even root function because, if you say it out loud, that is the square root of x minus 1. So even though you don't see the index, it is a square root. That means it is an even root. And because this is the only function in the power and root family that we talked about, an even root is the only one of those types of functions that has a restricted domain. And so it's important, if you have a restricted domain, that you must check for extraneous solutions. You don't have to do it with every equation, But with the functions that have restricted domains, it's really important to check your answer to make sure it's in the domain. So let's go ahead and do this problem. Again, I want to isolate the square root, so I'm going to do that by subtracting 18. And so I'm going to have the square root of x minus 1 is equal to negative 10. And so now I've got to think about how am I going to undo a square root. So if I'm taking a root of 2, the way I'm going to undo that is to raise it to the second power. So if I do it to one side, I also have to do it to the other. And this is a really important thing. So remember how in the first problem how we had the negative inside or outside of the parentheses? If I want to square negative 10, you need to make sure that you put parentheses around the whole number when you square it. That way, my square root and my square ultimately cancel each other out, and I'm going to be left with x minus 1. And when I square a negative 10, I'm going to get a positive 100. Next thing I want to do is add 1, and that way I'm going to get x by itself. And I find that x is equal to 101. But I do need to check, since this was an even root, we said it's possible for there to be an extraneous solution. So this is where I'm going to actually go back to my original problem, and I'm going to plug the 101 in. So my original problem was x minus 1, or the square root of x minus 1. So I'm going to go ahead and put my 101 in there, subtract the 1. I've got a plus 18, and I want to see if that equals 8. I'm going to put a little question mark there because I'm not sure. Well, 101 minus 1 is 100. So now I need to take the square root of 100 plus 18. Well, the square root of 100 is 10, and 10 plus 18 is 28. And 28 is most certainly not equal to 8. So that means that this answer, this x equals 101, is actually an extraneous solution. It turns out there is no solution to this equation. And if we go back to the original equation and we kind of think about what this would look like graphically, it might make a little sense as to why there's no solution. So if you think about, we said this graph right here represents our parent function. So if I think about each side of this equation as a different function, and I graph it separately, if I think about the left-hand side, the h value in this case is a 1, because if you look underneath the square root, that's x minus 1. So that means that we're shifting the graph to the right 1 unit and up 18 units. So let me draw a picture of what that would look like. So I want to go to the right 1 unit, and I want to go up 18. I'm just going to pretend that's 18. So that's where the beginning of my graph would be, and it's going to go up and over. It's going to be like that half of a parabola that's been flipped on its side. If I think about what's going on the right-hand side, that's just 8. Y equals 8. So y equals 8 is going to be somewhere in here, and that's going to be a horizontal line. And if I graph it, I think it's pretty obvious that those two graphs are never going to intersect. And so this would be an example of why we have an extraneous solution. Okay, so I showed you a little bit with the graphs. In number 3, we're going to do a little bit more with graphing. You'll see that there are 2 equations and 2 graphs, and some of the questions that you're asked have to do with the domain and the range. There are several questions on the quarterly that require you to define the domain for a different function. And so it's important that you remember all those AH and K transformations. Remember, it doesn't matter what the shape of the graph is, so let me just do a quick review. Let's say our function f of x, and it doesn't even matter what it looks like. So I'm going to make my function f of x, I don't know, I'm going to make it look like a check mark. I'm going to make it look like this. This is f of x. So if I were to do something like, I don't know, let's do it in red. If I were to do something like take the negative of f of x, that is going to reflect my graph over the x-axis. So now it's going to look like this. That's going to be my new, that's going to be the opposite of f of x. I'm reflecting it over the x-axis. Well, what about, let me go ahead and erase this. What about if instead I did f of x and I added a number? So let's say I add 2. Okay? So what that's going to do to my graph is it's going to shift it up 2 units. It doesn't matter what the shape of my graph is. That's going to be my f of x plus 2. Okay? if I were to do something like f of x minus 3, when it's inside the parentheses, it's affecting my x value. And so this is actually going to shift my graph to the right 3 units. And so now my graph looks like this. And so all I've done is I've performed the AH and K transformations on some other function. It doesn't matter what kind of function you're dealing with. So it's important that you remember that those transformations, so in general it looks like this. Those transformations are going to be consistent with any function you deal with, whether it's a sine function. Remember the k value on a sine function was the midline. It shifted it up or down. It doesn't matter if you're dealing with a quadratic function where it looks like a parabola, or like we've seen with rational functions. Like the AH and K transformations are the same regardless of the function you're dealing with. So keep that in mind. So let's go ahead again and take a look at this table. So the equation where we have a number in the first one is y equals x squared minus 2. I'm going to take a look at that exponent. It is clearly just a power, and it's an even power. So I'm going to go ahead and just fill in this part of the graph. It's a power, and it's an even power. And I know from what we did in the beginning of the year that when I have an x squared, that's going to be the shape of a parabola. And if I want to figure out where to graph it, if I can identify the values of AH and K, it'll help me. So in this case, my A value, that's the coefficient of x squared, is just 1. Since I don't have anything inside that's being squared with x, that tells me that my h value is just 0, and my k value is negative 2. So when I'm graphing my parabola, I'm going to plot my vertex at the point 0, negative 2. Because a is 1, I know that my graph is going to be opening up, and it should be congruent to the parent function. So that's essentially what it's going to look like. I know that the domain for any quadratic function is going to be all real numbers, but I can also say that the range is going to be limited. It's going to be restricted because I have a minimum on this graph. The minimum of my graph is negative 2, and all my y values are above that. So one way to express the range would be to say that y is greater than or equal to negative 2. You also need to get in the habit of using the interval notation, what you see here. Okay, so if the domain is all real numbers, another way to express that is to say that my domain goes from negative infinity to positive infinity. And we use the parentheses when the boundary isn't fixed. So for example, negative, I can't actually ever reach negative infinity or positive infinity. If there was an equal sign, if it was a number, for example, in the range where I have y is greater than or equal to negative 2, that means that y can go from negative 2 to positive infinity. It's never going to reach positive infinity, so I use that kind of like that curve as my boundary. But because it's possible that y equals negative 2, instead of using that parentheses, I'm going to use a bracket. And that's equivalent to the greater than or equal to. That lets me know that the boundary of negative 2 is something that y could actually equal. Let's take a look at the next one. I'm going to look at that exponent, and I can see that it's rational because it's a fraction, 1/3. Well, another way to express an exponent of 1/3 is to think of it as a root. This is the same thing as the negative cube root of x plus 1 minus 1. And so I can see that this is an odd function because that 3, that index of 3 is an odd number, and it's a root. Remember, if I'm looking at my rational exponent and there's a number underneath the fraction bar, that's underground, it's a root. So my third root. And if I think about what that graph looks like, it's going to be that S shape that we're familiar with, odd functions, but it's going to be an S that, and I'll just go ahead and plot the parent function. It's going to be a sideways S that passes through the origin and increases. That's the parent function for the cube root of x. So if I take a look at my transformations, again, I want to identify the values of h and k. Well, h in this case, well, let's do all of them. So a in this case is now going to be a negative 1, which tells me that I need to reflect that graph. My value of h is also negative 1, because remember, if underneath the quantity is x minus h, so I have to take the opposite. And then my k value is also negative 1. So I'm going to go ahead and start by plotting my negative 1, my hk. And then when I construct my graph, I find it easier, instead of trying to draw the graph all at once, I think it's easier to draw it in pieces. So I'll draw the left side and then the right side. And because my graph is reflected, I know that ultimately it's going to be decreasing. So on the left, it's going to be kind of an S shape going up this way, and on the right, it's going to be going this way. When it comes to the domain and range, what's really nice about our odd powers and roots is that there's no restrictions. Ultimately, they're going to hit every number on the x-axis and every number on the y-axis. So in both cases, our domain and range is all real numbers, and that's the shorthand for all real numbers. If I wanted to write it as an interval, I would say that it goes from negative infinity to positive infinity. You don't need the positive sign when you're writing infinity. If we take a look at the third example, this function is just presented graphically. I can see that it's that S-shaped graph, so I know that tells me it's an odd function. The fact that it's going up and down tells me it's actually going to be an odd power. And again, like we said before, with the odd functions, my domain and range are both going to be all real numbers. There's no restrictions, so that makes it really easy. There's nothing special that you have to remember. So let's think about how we're going to construct the equation. I know it's going to be of the form where y equals, and then I'm going to have x something to the third power. So I've got to figure out my values of a, h, and k. Well, the values of h and k are going to be determined by this point of inflection here. This is the point where the graph actually changes concavity. It doesn't change direction here. That happens in a parabola. So in a parabola, the vertex is where the graph changes direction. But a point of inflection is where, if you notice, here the graph is kind of curved down, but on the other side it's then curved up. So that point is where the graph changes concavity. It's called a point of inflection. And the ordered pair here is 1, 0. Well, this gives me the value of h and the value of k. I think in the directions you're told that the value of a is either a positive or a negative 1, so you don't have to worry about identifying the dilation if it's stretched or compressed. It's either going to be positive 1 or negative 1. So now I just want to look to see if the graph is increasing or decreasing. And because this function is increasing, I know that the value of a must be a positive 1. So now I'm just going to put all that stuff together. The value of a is going to go out in front. My h, remember it's always in the pattern, it's x minus h, so I'm going to have my x minus 1. And then I'm going to have my k, which is 0, so that would be like adding plus 0 on the end. But oftentimes we rewrite this as x minus 1 cubed. You don't see the 1 in front or the 0 constant because they don't affect they don't affect the pattern. All right, and then finally, in this fourth graph, we already saw in the previous example when we were solving excuse me, when we were solving number 2b, what the square root function looks like. And I think you can tell from that last graph that this is a square root function. So that means if it's a square root, we already are told that it's even, but we also know it's going to be a root. Okay. One of the things I want to do is identify the values of a, h, and k from the graph. And so if I look at this point, that's going to correspond to the values of h and k. So that's going to be negative 2. Positive 3. So that gives me my h and my k. I can see that this graph is decreasing, so that means the value of a is going to be a negative 1 this time. And if I'm thinking about my range, so we're given the domain is that x is greater than or equal to negative 2. And notice again that I've got that bracket and the parentheses. So negative 2, because it is actually a boundary point, it's included in the graph. I use the solid bracket, and since infinity actually isn't a number that we can reach, we use the curve. So my range, notice since the graph is going down, y is going to be less than or equal to 3. That's the y value, or it's going to correspond to my k value in the vertex. And so if I wanted to express this time I have to be careful because we're typically, we put our number first, but if I think about it, if I think about a number line and what this looks like, here's 3, and if I were to graph this, I'd have a solid point and I'd be drawing an arrow to the left. So if I think about what the low bound is, the low bound is going to be negative infinity. So when I express this using the interval notation, I'm going to have my negative infinity first and then the 3. So you do want to make sure that your numbers are in order like they would be on the number line. Again, because it's never actually going to hit negative infinity, I use the curved bracket or the parentheses, and since it can equal 3, I'm going to use that hard, the bracket. So when I write the equation, Again, we already know it's an even root, so if I just kind of write the skeleton of the equation, it's going to look like this, with the x underneath. Because a is -1, I know I can put that out in front. My h value is -2, so when I do minus a -2, that's the same thing as adding 2 to x, and then I'm going to have my +3 on the outside. And again, we don't actually need to put the 1 there. You can just write it as negative square root of x plus 2 with the +3 on the outside. Okay, the next section of the review deals with inverse variation. And this gets us into starting to talk about rational functions. When a quantity, or when two quantities vary inversely or are not proportional to one another, it basically means that as one quantity increases, the other is going to decrease. And you can look at this either in two different ways. Oftentimes we say if two quantities are varying inversely, then x times y is going to equal some number. And if I were to solve for y, then I would just divide both sides by x, and I get that y is equal to a over x. And if you were to play around with this, if I keep a as a constant, we call this the constant of proportionality. So if I were to increase the value of x, imagine what would happen as that denominator, as I keep dividing by a larger and larger number, it's actually going to make that quantity smaller. So as x gets bigger, y is going to get smaller. And vice versa, as x gets smaller, y is going to get bigger. And that's what we mean by that varying inversely, or inversely proportional. Sometimes you'll see it written both ways. So in number 4, this is just sort of a naked problem. It says, suppose y varies inversely with x, and when x is 6, y is 4. So if I want to figure out what that relationship is, I've got to figure out what the constant of proportionality is. And again, all we have to do is multiply x times y to get it. So if I know that x is 6 and I know y is 4, that gives me the constant of proportionality, which is going to be 24. So if I want to write an equation to relate x and y, so if I know that x times y is 24, and I solve for y, then I know that y is going to be 24 over x. So when it's naked, it doesn't really, I don't know, it doesn't really make a lot of sense to me. But when I think about it in context, I think it makes more sense. So it says the number of hours to construct a deck, and we'll call that y, is inversely proportional to the number of people available to construct it. I mean, doesn't that make sense? The more people that you have available, all hands on deck, right? The more people you have available, the less time it's going to take. So there's a relationship there, though. So if it takes 4 people that can construct, this should say a deck, not a house. Sorry, whoops. Whoopsie. Okay, so if it takes 4 people 12 hours to construct a deck, let's think about what the constant of variation or the constant of proportionality is. They mean the same thing. So we know that if we said that x represents the number of people and y represents time, and I know that x times y is equal to a, if it's a inverse proportional or inverse variation, and I know, so let's say if we have 4 people, that's going to be x times 12 hours. Well, 4 times 12 is 48. That means that my constant of proportionality or my constant of variation is going to be 48. So if I want to write an equation to represent this, well, if x times y is equal to 48, that means that y must be equal to 48 divided by x. So now, if I have 6 people available to construct the deck, I can estimate how long it's going to take. It shouldn't take quite as long because I have more people doing it. So if I plug my x equals 6 into this equation, I find that y is equal to 48 over 6, and 6 goes into 48 8 times. So if I add 2 more people to help me build this deck, it's going to take me 4 less hours to do it. And that's assuming, obviously, that they work at the same rate as everybody else. But I think when you look at inverse variation in context, it makes a little bit more sense than it does when you're just looking at the naked numbers. Okay. The next thing we want to take a look at, whoops, there we go. Next thing we want to take a look at are the graphs of rational functions. And there's essentially 2 different forms of the graph and of the function that we explored in this unit. One was in the AH and K form. So sometimes you see it with the A out in front, sometimes you see it as part of the fraction. So this would be looking at our rational function in that AH and K form. The other is when it's written as the division of two polynomials. So you might see something like this, where it's something in standard form, a polynomial in standard form, divided by another polynomial in standard form. And so we need to be able to understand the function no matter how it is depicted, and we want to be able to graph it either way. So if we start with the AH and K transformations, we can just go back to what we did in the last grid. So if I can identify which functions are which, or which graphs, or which format these are in, let's call this format A and this format B. Okay, so I have three different equations here. I'm going to have to produce two graphs, and one of them I'm given a graph, which is nice. So if I take a look at this first equation, that's going to be in that first form, my AH and K form. In the next two, these aren't actually written in the standard form because I've already factored things for you, but it is essentially going to be in that second version. It's just factored for you to make graphing it a little bit easier. So in the first one, I want to identify my A, my H, and my K. And if you remember the parent function for a rational function, we have asymptotes at x equals 0 and y equals 0. And the graph itself is just two sections of a curve in the first and third quadrants. So if my A value was negative, I would just reflect that whole graph. And so therefore the two sections would then be in the second and the fourth quadrant. My H value, again, it's going to shift the graph left and right. So it's going to shift my vertical asymptote left and right. And the K value, which shifts the function up and down, is now going to shift my horizontal asymptote up and down. One of the things that I think is helpful when I'm graphing these is to note that the point where my two asymptotes intersect corresponds to the H and K values. So sometimes students get confused about which is the vertical and which is the horizontal, but I think if you can identify H and K, then you can very easily draw a vertical line and a horizontal line through that point. So let's do that first. I think we can see that my A value up here, that's my A value. My A value is positive 1, so that means that when I graph it, the two sections are going to be in the first and the third quadrant. My H value, remember the quantity x minus 1, x minus h. In this case, h is going to be a positive 1, and k is going to be a positive 2. And again, like what I think is helpful is to plot the point 1, 2. So I'm going to go over 1 and up 2. And that's the point where my two asymptotes are going to intersect. My function is actually not going to go through that point, but it does help me when I am constructing my asymptotes because I can just draw the vertical and the horizontal line. It makes it a little bit easier for me to see. I can see my vertical line is this one that goes up and down, and I can see very clearly that it crosses through the 1. So that is going to be my x value, my vertical, which is kind of counterintuitive because it's the y-axis that's vertical, but that when x is 1, it means y can be any number. X in this case is always going to be 1. My horizontal asymptote is going to correspond to the 2 on the y-axis, so y is equal to 2. That means my function is not going to touch or cross it. All right, so my domain, since I have asymptotes here, I know that my domain then can't equal 1. It's never going to equal 1, and that's one way to express it. The other way to express it is to recognize that there are going to be two sides, and so since we haven't reflected it, let's just go ahead and sketch what that's going to look like. So I know that on the left, my function is going to go from negative infinity to 1, but it's never going to actually touch 1. So when I do this, I want to make sure that I have negative infinity to 1, and I'm going to have the curved bracket on either one. But I also know I have another section of the graph where my x values go from 1 to infinity, but again, it can't actually equal either one of those numbers. So I say union 1 and infinity. For my range, it's very similar. Because I have a horizontal asymptote at 2, I know that y cannot equal 2. None of my y values can ever equal 2. It'll never happen. So again, if I go in order, that means that y can be anywhere from negative infinity to 2, or it can be from 2 to positive infinity, and that's how I would express my domain and my range. When we get into the second form of the equation and we factor it, and so you'll notice that both of these expressions are already factored for you, we also have to contend with holes in the graph. And holes in the graph occur when two factors cancel. So if I take a look at the first example, notice that there's an x minus 3 on top and an x minus 3 on the bottom. Those expressions cancel, but they were part of my original function. And so if I think about what would happen if x was 3, if I plugged a 3 into the original equation, I'd end up with 0 times 5 over 0 times 4. Well, either way, I'm going to end up with 0 over 0. Try plugging that into your calculator. In fact, I have my calculator right here. If we take, excuse me, if we take 0 and we divide it by 0, you will get an error message. It's not possible to divide by 0. It's undefined. And so my function cannot exist at 3. And so we say that there's going to be a hole at 3. And the way we find our holes, let me erase this real quick and write it again. The way we find our holes is when there's an expression that cancels. Sorry, my board sometimes gets a little wacky. When there's an expression that cancels, we want to set that expression equal to 0. So if I have x minus 3 and I set it equal to 0, I get 3. Well, that actually tells me that my function cannot equal 3. So I actually probably want to set it not equal to 0. And that's going to be a hole in the graph. And I think you can see when the value of x is 3, I have a hole in the graph, and you can actually see it. On your calculator, if you were to graph this on your calculator, it doesn't plot the hole the way you're seeing it here. But if you were to move your cursor, or if you were to look at the table, you would see that when x is 3, you get an error. So I want to think about what's left. My vertical asymptote is found by taking the remaining quantity in the denominator, that x plus 1, I'm sorry, my board is not calibrated anymore. Okay, so to find the vertical asymptote, I'm going to take what's left in the denominator, that x plus 1, and set it equal to 0. If I subtract 1 from both sides, I get x is equal to negative 1. And again, if x were to equal negative 1, I'd end up with 0 in the denominator. And that, again, is not allowed. So that tells me that I have to have an asymptote at x equals negative 1. You also learned a rule when you divide. So if you take a look at the ratio of the coefficients, that helps you find your y asymptote, or your horizontal asymptote. I think from the graph you can see that it's 1. But if you had to do it algebraically, you'd have to think about what this function looked like originally. So if I thought about it, if I were to FOIL things out or multiply and distribute things out, I'd end up with y is equal to x squared minus x minus 6 over x squared minus 2x minus 3. And so what I'd want to do, since the powers of my x's is the same, and the coefficients in both cases are 1, if I divide, I get 1 over 1. And that's where that horizontal asymptote of 1 comes from. So if I think about my domain, I've got to be careful because x cannot equal negative 1, but it also can't equal a positive 3. So I've got 3 sections to my graph that I have to think about. So x can't be, let me write this down, x can't be negative 1 or positive 3, because that's where my hole is. So when I write my interval notation, that means that x can go from negative infinity to negative 1, or it can go from negative 1 to 3, or, so that's the u, or the union, or 3 to positive infinity. And so I'd have 3 different intervals on which x could exist. When it comes to the range, and you're not going to have to do this, when it comes to the range, you'd actually have to figure out the corresponding, what y would be if that quantity wasn't there. And so if you divide what's left, so when x is 3, if I think about the quantity that's left, that x plus 2 over x plus 1, and put a 3 in there, that would leave me with 5/4. And so that would be the y value in the whole. You don't need to do that for the quarterly, so I'm going to show you how to do it. But so I know that y can't be, if I think about my asymptote, it can't be 1 or 5/4. And 5/4 is 1.25. So it can't be either one of those numbers. So if I were expressing the range in this interval notation, again, I would go from negative infinity to 1, union 1 to 1.25, union 1.25 to infinity.